Welcome back. It is day 3 of Carbohydrates. We're going to discuss a couple of things today. We are going to discuss disaccharides, cyclizing sugars, and finally we are going to talk about derivatives of sugars. All of these things we talked about in greater detail in lecture, but I just wanted to give a brief little review over this content. So on this first slide, I wanted to focus a little bit on, or primarily I wanted to focus on cyclizing and aldose. What we have here is glucose, and then what we have here and here are the two results of the cyclization of glucose. Now, one of the things that I want you to keep in mind, and one of the recommendations that I make, is always know a staple molecule. If you know that, then you can relate that to other molecules. You can relate it to the cyclized form of that sugar, or you can relate it to epimers and the cyclized form of different epimers. So what we have here is glucose, and it is an aldose. One of the things that I want you to keep in mind is, since this is D-glucose, we know a couple of things about it. First and foremost, we know that carbon number 5 has our hydroxide group on the right-hand side, given that it is a D sugar. Now, as it is glucose, one of the things that you should know is that this is an aldohexose. So as an aldohexose, you know a couple of things. It's going to have an aldehyde group, carbon number 1, and as a hexose, it is going to have 6 carbons. So 1, 2, 3, 4, 5, 6. So when you start out with a name like glucose, I want you to be able to very quickly fill in what that means and what that molecule looks like. And I also want you to distill it down. Ultimately, when it comes to drawing glucose, all that you need to know really is the orientation of our hydroxide groups about carbons 2, 3, and 4. Because everything else has been given to you basically by the name. The D sugar tells you that the right-hand side, or the hydroxide group on carbon number 5, our penultimate carbon, is on the right-hand side. You do have to know that glucose is an aldohexose, but once you get beyond that, then it's kind of just a matter of, well, remembering the positioning of 3 hydroxide groups. Okay, so with that said, we can cyclize a sugar into 2 different orientations. We can cyclize a 6-carbon sugar into 2 different rings. What we've chosen to do here is we've chosen to make the pyran sugar. So the pyran sugar is going to have 6 atoms in the ring. One of them is oxygen. What that means is whenever one of those atoms is oxygen, then you have this 6th carbon that is, well, outside of your ring. Okay? So what I would like you to do when it comes to knowing the structure of linear glucose versus a cyclized glucose is put things into perspective. Carbon number 1 is your aldehyde group. That's going to be right here and right here. Okay? Now, the variation about carbon number 1 is this hydroxide group. That hydroxide group is going to be up or it's going to be down. And what I like to look at this as is compared to carbon number 6. Okay, so if what I like to do, and the way that I like to think about this, is if your hydroxide group is down and your C6 is up, then this has all the makings of these 2 atoms being in trans, or these 2 groups being trans to one another. And if they are trans to one another, what does that mean? That means you're dealing with an alpha sugar. Now, the opposite, therefore, is also true. If OH is up and C6 is up, all with respect to the ring, well then, these 2 groups are cis one another. And if they're cis to one another, you are talking about a beta sugar. So we have 2 different variations of drawing a well, drawing a cyclized sugar. Now, what I would then do after that, after I've established if I'm drawing an alpha or a beta sugar, or if I'm looking at an alpha or a beta sugar, what I would do is look at, well, which are the carbons that I actually care about? When we were drawing, or when we were talking about our linear form of D-glucose, we cared about carbons 2 through 4. When we look at our cyclized form of our sugar, well, where is oxygen from carbon number 5? Well, that's right here. That's right here. That's the 6th member of our ring. So when it comes to altering the orientation of hydroxide groups, well then the only 3 that we're going to be altering are on carbons 2, carbon 3, and carbon 4. Carbons 2, carbons 3, and carbon 4. If you notice, carbon 2, 3, and 4 are identical in the alpha D sugar and the beta D sugar, which makes sense because alpha versus beta designation only relates to carbon number 1. Now, with that said, the reason I talk about a staple molecule is I want to be able to refer to the linear sugar and the cyclized sugar and know what I'm talking about. What I always do is I look at D-glucose in the linear form and I say carbon 2 is hydroxide is on my right, carbon 3 hydroxide is on my left, carbon 4 hydroxide is on my right. Okay. Now, the staple molecule for this, the cyclized sugar, I've got, so I'm going to write linear. Cyclized, I've got carbon number 2, which my hydroxide group is going down. Carbon number 3, my hydroxide group is going up. And carbon number 4, my hydroxide group is going down for the cyclized form. So the way that I look at that is if it's on the right-hand side, I'm talking about a cyclized, or sorry, if I'm talking about my linear sugar and my hydroxide group is on the right-hand side, then when I cyclize, right is equal to down. Left is therefore equal to up. So that's what I'm going to do whenever I'm going from a cyclized form to a linear form. I hope this is a helpful look at your different sugars and cyclizing a linear sugar. On to the next part. So this next slide is a look at the different fates of sugars. For instance, one common fate is that a sugar can be reduced to form a sugar alcohol. Sugars can also be oxidized to form lactones. And then finally, this is kind of an example of reduction as well as it can be done independent of reduction, and that is phosphorylation. This is particularly important whenever it comes to a discussion of metabolism. Specifically, glucose metabolism and central metabolism in the process known as glycolysis. Glycolysis is the process by which glucose is converted, Glucose, is converted into pyruvate, and you generate some ATP, adenosine triphosphate, the molecule that, well, basically gives you energy. I really wanted to just talk about this to discuss some of the different fates of sugars and some of the, I guess, results of sugars. So keep that in mind. Now the last point that I really wanted to discuss here in this, or that we discussed in lecture, was the production of disaccharides. So what we have here is glucose, and we have CH3OH. This is going to serve as our alcohol. And what we're able to do here is use this alcohol to substitute the CH3O group for our hydroxide. So what that results in ultimately is the production of H2O as well as a glycosidic bond. So our glycosidic bond is going to be carbon number 1 to an oxygen to CH3. Now what this can be is, this can be the alpha designation So our carbon number 6 is up, and carbon number 1, or well, yeah, our carbon number 1 is down. Or they can both be up and up, in which case they are cis to one another, and we've made a beta sugar. So this glycosidic linkage, or glycosidic bond, which I want to say glycosidic bonds, or that term, I will use interchangeably with glycosidic linkage. I'll use those interchangeably. Well, what's significant about that is this isn't necessarily just the addition of a methyl group to a sugar, but instead this is much more relevant whenever we come to discuss di and polysaccharides. If you look on the next slide. So what we have in this slide is the combination of alpha D-glucose and beta D-glucose. We have two groups that are going to participate in the chemistry here. We've got a hemiacetal and an alcohol. Just like we saw on the previous slide, rather than having CH3OH as our alcohol, we have an entire sugar. Okay. Now, what we need to do is orient ourselves with respect to our alpha designation and our beta designation. We have the addition of two different glucose molecules. One is alpha D-glucose, one is beta D-glucose. In a condensation reaction where we're going to produce some H2O, we have the formation of an acetal and a glycosidic linkage. Okay. Now, when we look at this molecule, this resulting product molecule, what we need to do is look at our name. Our name is alpha D glucopyranosyl 1,4-D glucopyranose. Okay. This shows us a couple of things. First of all, alpha. What is that telling us about this molecule? That's telling us that we have an alpha glycosidic linkage. Okay. After that, what are we told? We have 1-4, meaning that our glycosidic linkage is between carbons 1 and carbon 4. Okay. So if we look at these two different sugars that we're talking about, we've got our anomeric carbon, carbon number 1, linking to carbon number 4 of our adjacent sugar to make up our maltose molecule. Now what I'd like to draw your attention to is the result. Okay, so we have a couple of different things that we need to look at. First of all, we have a hemiacetal. Now when we look back up at the starting reaction, what did we have? We had a hemiacetal. Our product gives us a hemiacetal. So a natural question is, could we form another glycosidic linkage? And the answer is yes. What would we need? We would need another alcohol, or need an alcohol. Sorry about that. Alcohol. So we'd need another sugar. If we add another glucose molecule, then we would make a trisaccharide. So we have a number of different options that we can use this molecule for. And this alpha designation at the front tells us the orientation, or tells us if we're dealing with an alpha or a beta linkage for our glycosidic linkage.